Assalamualaikum and good morning. My name is Ruslizam Daud, and before I start this sharing session, I would like to thank to MACE, Malaysian Society for Automatic Control Engineers, and also Center for Artificial Intelligence and Robotics UTM, Cairo, giving me opportunity to share with you about the ongoing research to measure implant stability. The research on implant stability is part of my PhD student works, and she will closely work with orthosurgeon from HUKM, Hospital University Kebangsaan Malaysia, and also Hospital Tengku Fauziah, because the orthosurgeon always requests about additional information or data that can support their decision to make the right clinical loading fixation, and that refer to external fixator. Let's have a brief introduction about bone fracture. For example, long bone fracture, we can see so many type of bone fracture. We have oblique, we have transverse. What I would like to pinpoint here is about having micro motion model, or do the modeling works that consider the micro motion, and it refers to the gap between the fracture surface for every bone fracture, and that will determine the ongoing stability as the bone go through osseointegration process. Let's have a brief about fracture healing, and let's look at figure 2. The day of injury or the day of bone fracture will undergo 2 weeks, 6 weeks, and 3 months, and there we can see the formation of soft callus and hard callus before the formation of full hard and rigid bone in 1 year and 2 years time. The things that I want to highlight here is if we able to model the soft and hard callus formation in any prediction of bone healing, for sure we can configure the accurate primary and secondary stability of the bone, and that refer to fracture stiffness and stability. Let's talk about implant stability. We have two kind of implant stability. We have primary stability and we have secondary stability. What is primary stability? Primary stability comes basically the first day of mechanical engagement with cortical bone, and that refer to the bone quality, the surgical techniques, and also the implant geometry that refer to diameter, the shape of the implant or the design of the implant, and also the surface characteristic as well as the material of the implant. And secondary stability will refer to how the regeneration of the bone or remodeling of the bone, and also the tissue around the implant will be formed, and that means the secondary stability really depends to how good the primary stability being configured by the orthosurgeon. It means the technique, it means the implant use, it means the bone quality that time. Okay, look at the figure 3. We can see clearly how the primary stability will determine the goodness of the secondary stability, as the formation of soft callus and hard callus from the first day of the bone fracture until it the bone healing will complete basically between 1 or 2 years. Look at the table 1. We can see 4 invasive or destructive method being used just to measure the implant stability. And taking example of tensional test means that there will be direct contact with the patient, as well as pull-out test, and maybe the surgeon need to do a kind of minor surgery just to check the implant stability. And we really not interested in that method, but we really interested in try to use finite element analysis to find ways how to measure the ISQ or implant stability, so that we can predict the value of implant stability, or the stability of the fixation before the bone implant fixation being made by the surgeon. And that will be continuous monitoring is important to determine the status of implant stability, as for now there are no such comprehensive continuous monitoring method that can be used. Once the internal fixator, as shown in figure 4, installed in human femur bone, if we can monitor the process of bone healing, and we can avoid of having the failure of the implant screw, as shown in figure 5 and figure 6. And talking about this, if we can monitor the implant stability, we also can monitor the process of osseointegration process. Figure 7 shows the example of FE model from previous literature, and what I want to highlight here, none of them concentrate on how to come up with stability value, or how to configure the primary stability of the fixation in regards to the formation of soft tissue and hard tissue. Let's go straight to the research that we have been doing in our research group. Basically, we refer to the 3 kind of stability. We have absolute stability, relative stability, and instability. We try to relate to implant stability quotient, ISQ, and we also try to make use or develop the algorithm to, at the end, having the value of ISQ between 0 to 100. And figure 9 shows how we do the setting for the internal fixator having 1 plate and 6 bicortical screws. We try to simulate 3-point bending and 4-point bending in regards to the way how the load for every single screws, which involve shear, oblique, and pull out. And we try to consider also the properties or the formation of soft callus and hard callus between the fracture surface. Okay, talk about the modeling method. We try to consider every possible configuration as shown in figure 5, and we set the boundary condition, and we refer to the AO classification, and we also refer to the auto surgeon just to make sure that we work within the specification of clinical requirement. And Figure 12 shows the result of this study, and as we can see, based on the 4 finite element model D1, D2, D3, D4 that refer to 4 different bone density and 4 different Young modulus. As we can see, based on the normal, oblique, and shear loading, this study result managed to categorize the stability based on 3 states: low stability, medium stability, and high stability. Good about this data is that it can provide information based on the implant fixation configuration. The surgeon may able to decide what will be the best sequence, what will be the screw and implant loading experience, what will be the best gap between setting between two fracture surface to promote fast, soft, and hard callus formation. What will be the best material for the implant material to be used? Maybe what will be the best geometry of the thread and the diameter of the screw? What will be the best locking and unlocking system of the screw, and many more. Before they do the actual operation, just to install the internal fixator for implant bone fixation. And I believe this data can be refined more so that the accuracy wise will be confirmed. And good about this, if we can find agreement with any existing method being used in hospitals, for example, or by doctors, that we can see whether is there any errors based on the ISQ value that's been made reference in hospital. Before we end this training session, I would like to share with the audience that we are now still doing research on influence of micromobility of perfect fittings, and also effect of loosening gap on primary implant stability. And based on our reading, we also come across to many interesting study that relate to implant stability, since the area of expertise not fall into our mechanical background. It's maybe those from mechatronic or electromechanical background can venture into electronic technology resonance, for example, and also magnetic technology resonance, to get the value, to develop the device or algorithm to get the value of ISQ, and so we can collaborate or compare the data from finite element analysis, and at last we can also support the auto surgeon to have the best setting of the fixation before they do the actual implantation or do the actual implant installation, and they can have the best implant stability and promote the best bone healing for the patient. With that, I would like to end my presentation, and please forgive me for any weaknesses during my presentation. I believe we can improve further, and Assalamualaikum. Terima kasih.